All right, so welcome back to Banff, everyone, and thank you. I got a whole bunch of projects on Tuesday, and I expect to have the. So I have also good news, which is that I discovered sort of late in the game that Fields Institute has provided a little bit of money for a grader, and so I now have a grader, and I expect assignment 2 will be graded very soon. And I also expect to get you feedback on your projects next week sometime. Okay. Right, so I think I just introduced epsilon isometries at the end of the previous lecture, and I was planning to use them to prove the following theorem, which is from Barago, and Ivanov, which basically says whenever you have compact metric spaces, if the Gromov-Hausdorff distance between them is 0, then X is isometric to Y. And this is actually the last. Okay, so let me prove the theorem. And so one of the things that compactness gives us is that that we can find a dense countable subset of X. So of course we'd have that for X just Polish, but anyways. And the Gromov-Hausdorff distance being 0 implies from the last lemma that we talked about in the previous lecture that for every epsilon positive, there exists an epsilon isometry. So let's say, in fact, let's do it for, let's say for every natural K, there exists a 1/K isometry. Fk from X to Y, and recall that what that means is that on the one hand, the distortion of the graph of Fk is less than 1/K. And on the other hand, it means that the image of X under Fk is a 1/K net in Y. Okay, great. So if I set Y and K to be the image under Fk of Xn for every K and N, by compactness of Y, that if I fix one of these natural numbers, there exists a subsequence in K with Y and K going to some limit depending on N along the subsequence. And so using a diagonal argument, I can extract a subsequence from all these subsequences, which is going to converge both for K and N. So so let's say Y and Kj such that the limit is J going to infinity of, and I'm probably not going to bother to relabel in the future, but anyhow. Right, so these subsequences over here depend on N, but this one doesn't. That's the point of the diagonal argument. And from this distortion condition, I'm going to deduce that, okay, so let's see, the distortion condition implies that the distance in Y between yn and ym, let's say k minus the distance in X between xn and xm is less than 1 over k. And so since these guys, this holds true for arbitrarily large k, I get that the distance between yn infinity and ym infinity is the same as the distance between xn and xm rather. And so basically what I've just done is set up an isometry. So I could if I set f infinity then what I've just shown is that the f infinity, at least on this preferred subset, maybe I should have given it a name. Let me call it capital S, is an isometry. Well, I guess it's an isometry onto its own image. But S was this dense set. And so you have this kind of one, and F infinity is one Lipschitz because of the isometry condition. So you can simply extend F infinity to the whole of X and still get an isometric map. Well, I guess it would be an isometry onto a subset of Y, but and then going back, because we knew that using the fact that these FKs form a 1 over K net in Y, we get that this isometry is actually onto. Actually, I mean, the way Birago and Rago do this last argument is they actually say, let's reverse the process and start with the start with this set here, which is the collection of yn infinity. And then we can define an inverse on this set, which is a 1 Lipschitz map. And so it extends to a 1 Lipschitz extension that inverts the original guy. And so so you see it's onto by that process. All right. And so once we have this, we already checked last class that the Gromov-Hausdorff distance satisfies the triangle inequality on compact metric spaces. And so, and it's clearly symmetric. And so by combining that with this, you get that it's actually gives a metric on isometry classes. Of compact metric spaces. Are there any questions about that? Okay, so I sort of mentioned when we were showing that the Hausdorff distance gives a metric on closed subsets of a given metric space. We kind of reduced it to this checking this finite thing. And now I'm going to talk about the analogous condition as giving a criteria for convergence, Gromov-Hausdorff convergence of metric spaces, not necessarily subsets of a given metric space, in terms of finite criteria. And so to do that, it's useful once more to introduce a couple of definitions. And let me, I have them somewhere. Let me pull them up for myself. Right. So we say metric spaces X and Y are delta epsilon approximations to each other if we can find subsets with the same number of elements finite, such that you can pair up these guys so that should xi, yi. So let's call this number n. And this should be a correspondence. So in other words, every x in x naught and y in y naught should be used at least once in this correspondence. With distortion less than delta. And so that's where the delta comes in. Delta's the distortion, and epsilon and x naught and y naught are epsilon nets in their respective sets. Sorry, in x and y respectively. Right, so I can divide the two metric spaces into some large, each metric space into the same large number of points. And I can set up a correspondence between the points on the left and the points on the right, which doesn't have a distortion bigger than delta, and such that the points are epsilon dense in their respective spaces. And maybe, I don't know, it probably doesn't matter, but I should probably make this inequality strict, but I don't think it matters. And the utility of this definition is that, oh yes, and then there's one more little, if you can take the delta equals the epsilon, then I'm going to drop the brackets. So if delta equals epsilon, we say x is an epsilon approximation of y, and but and so here's excuse me. Here's the utility of this definition. This is again a proposition from Barago and Ivanov. So given compact metric spaces, x and y, basically the existence of one delta approximates the other the closer, the better they delta approximate the epsilon delta approximate each other, the closer they are in Hausdorff distance, and vice versa. So if y epsilon delta approximates then the Gromov-Hausdorff distance between them is less than 2 epsilon plus delta. And conversely, if the Gromov-Hausdorff distance between them is small, then y is a 5 epsilon approximation to x. So if y delta epsilon approximates x, sorry, I keep reversing the orders. We just said that what that means is there's a relation R. With distortion less than delta such that, and projections which are epsilon nets in their respective spaces. And so, so the Gromov-Hausdorff distance between these subsets, these finite subsets, then, by our previous characterization of Gromov-Hausdorff distance in terms of existence of relations of bounded distortion, is basically, boy, I have in my notes it's delta, but I think it's 1/2 delta. Well, okay, so if it's 1/2 delta, then, so I think it's equal, yeah, it's less than 1/2 delta. So in this particular, it's less than delta. So that's for these finite subsets. And on the other hand, the Gromov-Hausdorff distance between X and its finite subset, because since X naught is already isometrically embedded in X, I can use just the ordinary Hausdorff distance between them as subsets of X, and that's at most epsilon, because an epsilon ball around all these finite guys covers X, and obviously X covers X naught. And so by the triangle inequality established last class for Gromov-Hausdorff distance, sorry, the same, of course, the same would be true with Y replace and Y naught. The triangle inequality for DGH now implies DGH of X to Y is less than this plus this plus this. So that's the 2 epsilon plus delta. And conversely, that's part A. So conversely, if this Gromov-Hausdorff distance is small, then there's a 2 epsilon isometry, which of course depends on epsilon, but from X onto Y, whose image is a 2 epsilon net in Y. And of course, because of the compactness of X, there's also an epsilon net, a finite epsilon net. In X. And so if I think if I set Y to be the image, Y naught to be the image of this epsilon net in let's see. Oh, sorry, yes, I'm going to set that way. But because part of the definition of being a 2 epsilon isometry is that the image under f of x is a 2 epsilon net in Y. And so then I claim that this set here is a 5 epsilon net. And let me see. So we already know that the distortion of, we already know from here that the distortion of F, or of graph F, is less than 2 epsilon. And so that also means that the distortion of the relation xi, yi is less than 2 epsilon. And so the only thing we need to, and this, if we project this onto the first coordinate, we have an epsilon net in X. And so the only thing to check is that the projection onto the second thing is a 5 epsilon net in Y. And then we've shown that there are 5 epsilon approximations of each other. And so let's see. So for every Y in Y, by this first condition, there exists an X in X such that the Y distance between Y and Fx is less than 2 epsilon. And because of the set of X naught is an epsilon net, there also exists an Xi and X naught such that the distance between X and Xi is less than epsilon. And by this distortion condition here, we have that the distance between Xi and Yi is less than 2 epsilon. And so when you add these three things up, you get that the distance between Y and Yi is less than 5 epsilon by adding these three quantities and using the triangle inequality. All right. So we've just shown the equivalence of convergence in the sense of arbitrarily good epsilon delta approximations and Gromov-Hausdorff convergence. And so basically what that allows us to do is to give a criterion for convergence of metric space, Gromov-Hausdorff convergence of metric spaces in terms of convergence of finite subsets. So this is Barago, and Ivanov, proposition 7.4.12, finite DGH convergence criterion. And so let's say if I have a sequence of metric spaces, of compact metric spaces, and a putative limit compact metric space. So n here will be any natural number or infinity. Then the Gromov-Hausdorff distance of the sequence to the limit is going to go to 0 if and only if for every positive epsilon, there exists finite epsilon nets both for the approximating guys and for the limit. Such that the Gromov-Hausdorff distance between the SNs and the limiting guy goes to 0. And moreover, these guys can all be chosen to have the same number of elements. At least if n is large. Okay. So in other words, when I want to check Gromov-Hausdorff convergence of something, it's enough for me to check it for finite subsets, provided the finite subsets can be taken to be sufficiently fine in the thing that I am sufficiently fine in the thing that I'm trying to check the Gromov-Hausdorff convergence of. And actually, I mean, there's, okay, yeah. So the direction that I really care about is this one. I really care about that when I check this for finite subsets, I get convergence to the limit. The converse direction is, maybe elegant, but not so crucial to me. And so let me do the proof in the direction I care about and leave the other direction as an exercise. So and I basically just want to use the criteria that we introduced in the previous lemma. So suppose, so assume for all epsilon, there exists Sn xn as above, such that the Gromov-Hausdorff distance of Sn in S infinity goes to 0. So what does that tell me? So that basically says the, oh yes, by this equivalence, since the Gromov-Hausdorff distance goes to 0, it tells me that these that implies by the previous proposition that is something like a 5 epsilon approximation. Epsilon, no, yeah. Sn is an epsilon approximation well, I should say rather, is an epsilon approximation to x infinity. Is that what I called it? Yeah. For n large enough, depending on epsilon. And then, but the previous proposition tells me that therefore the Gromov-Hausdorff, using it again, the Gromov-Hausdorff distance between xn and x infinity is less than 3 epsilon or something. And so therefore, but epsilon was arbitrary. So that this limit is 0. Questions? And I'll leave the other direction as an exercise. So this is the direction that I care about for the compactness theorem that I'm now going to hopefully state and prove. So this is Gromov's precompactness theorem for metric spaces. And oh yeah, so I guess I want a definition that I know we talked about totally bounded. I'm not sure we talked about uniformly totally bounded. So maybe I should give the definition first. So a class of metric spaces script x of metric spaces is uniformly totally bounded if and only if for every epsilon positive there exists n depending only on epsilon such that for every metric space xd in the class is covered by at most n delta n epsilon balls. Right, so totally bounded meant that for any epsilon, there'd be a finite number of balls covering my metric space. And what I want here is I have a collection of metric spaces, and I want the same number of balls to cover each of them. Great, and so then the theorem is that if you have such a class, of metric spaces, of compact metric spaces, is precompact in the sense that any subsequence has a Gromov any sequence has a Gromov-Hausdorff convergent subsequence. Any sequence of spaces xn dn in X has a subsequence with a DGH limit say admitting a DGH limit. Okay. All right, so this is the big result, let's say, that we've been aiming at for the last lecture in this one. So, oh, and maybe I missed oh yes, maybe I missed part of the definition of uniformly totally bounded. So first of all, it should have this uniform bound, and secondly, the maximum over all spaces in script X of the diameter of the space should be bounded. And I'm not too worried about point 2, because as long as I'm talking about geodesic metric spaces, or at least, yeah, or even metric spaces which are intrinsic, length spaces. So spaces where you can get the distance between any 2 points as an infimum of curves joining the 2 points, because when you can get the distance between any 2 points as an infimum lengths of curves joining the 2 points, then the length of such a curve is bounded by epsilon times the diameter of these balls, which is 2 epsilon, which is the diameter of these balls times the number of balls. And so then you get an automatic bound on the diameter. So 1 implies 2 in length spaces. But if I was thinking about spaces that aren't length spaces, maybe not even connected, then I want to impose this diameter bound separately. Okay, so let D and epsilon be the uniform bounds on diameter and size of epsilon nets in script X. And then I'm going to set N1 to be 1, and I'm going to define inductively for k bigger than 1, nk will be nk minus 1 plus the number of balls that I need to form a 1 over k cover. And so given any sequence of metric spaces, for every natural number, there's going to be a dense set I guess I should put brackets because it's an ordered set in Xn, such that the first nk points in S form a 1 over k net. In Xn, right? So the idea is that I mean, maybe so if you want, if you take your epsilon to be 1, then there's, maybe I should have taken this to be n1. I'm a little confused. Then the number of points I need is n1 to form a 1 net. And then you need some additional n1 half points to form a 1/2 net. And so you list the points for given the xn, you list the n1 points first, followed by the n1 half points that form the 1/2 net, followed by the n1 third points that form the 1/3 net, and so on. And in that way, you get an infinite sequence such that the first nk points form a 1/k net. And now I have this diameter bound. And so for every natural number I and j, the maximum over n of the distance between xni and xnj is always less than d. And these numbers, the distances are all non-negative. And so they all lie in this compact interval between 0 and d. And so that means that for any I and j, I can choose a subsequence of n along which these distances converge. This I have said this, yeah, it converges. And of course, the subsequence might depend on n, but using a diagonal argument, I can extract a further subsequence which converges for all n. This is not really, but yeah, that's what I would do. Sorry, it's crummy notation. So I probably don't want to reindex, so I won't reindex after this line. So let me call this d I. Well, this is just some. So this is just some number. So I guess I should call it d infinity ij. And so the Gromov-Hausdorff limit x infinity of xnm dnm is constructed as follows. So the first thing to notice is that d infinity satisfies the triangle inequality. On the natural numbers. So, the distance between I and j is less, the infinity distance between I and j is less than the infinity distance between I and k, and plus the infinity distance between k and j for any natural numbers I, j, and k. So it basically inherits the triangle inequality. D infinity inherits the triangle inequality from these guys. This is dnm, I guess. And so it's a symmetric, i.e., gives, and of course, it's always taking values in 0L, or 0D rather, as 0D valued semi-metric on N. And so you can, you basically can quotient out by any integers which are distant 0 to each other. So denote by I bar the equivalence class of natural numbers at 0 distance from each other. And then I have a metric space. So setting x infinity to be the natural numbers, maybe I should make this a tilde, quotient by this equivalence relation is a metric space for D infinity. And it may not be a complete metric space, but you can look at its completion. And basically, I claim that that's the Gromov-Hausdorff limit of these finite spaces. So it remains to show two things. Let me go back to the statement of the theorem. I think, yeah, so I think there was an exercise. If you read Biraga, you would have seen there was an exercise saying if you have a Gromov-Hausdorff limit of a sequence of compact spaces, the limit's also compact, but we'll get the compactness limit explicitly, I think, in this too. So it remains to show that that x infinity bar is compact. And that it really is the Gromov-Hausdorff limit of these approximating guys. And at least as m goes to 0 along the subsequence. Okay, so I'm going to suppress the relabeling now. Yeah. There's too many indices anyways. And for that, we're going to use this proposition that reduced checking convergence to these finite subsets. So the claim is that for every natural number k, if I set sk to be the set of sorry, hang on. Right, the set of equivalence classes such that k is no bigger than these numbers that I defined at the start, inductively at the start, that's going to be a 1 over k net. And basically by construction, that's true for the finite values of little m or n. And by the way, since this space is complete by construction, once I check that it admits a 1 over k net for arbitrarily large k, then it's compact. So I really need only to check the Gromov-Hausdorff convergence. Okay. So for every I, let's say, bigger than nk, and n in the subsequence, there exists an xnj in S and K with the n distance between xin and xjn less than 1 over k. And this, since the j here, although the j depends on I and n in principle, it's always less than n of nk rather, n sub k. For every I, there exists infinitely many n's with jin being equal to ji. Some so one pigeonhole principle says that as n goes to infinity, these j's are all bounded, and so infinitely many of them must fall into one of the classes, and let's call that the ji'th class. And so this is a subsequence in n, and along this subsequence in n, the distances converge. Between the equivalence class of I and the equivalence class of j bar of I, which is less than 1 over k. And so that, so therefore, the sk, which was the set of all these guys, is indeed the desired 1 over k net. And basically by the, okay, so now I claim the growth. So what we've just shown is that the Gromov-Hausdorff distance between the sk and the snk, or we haven't just shown it, but let's see. I claim that this goes to 0 by the convergence of these distances, which is, I mean, that's how we selected by this convergence here. So on these 1 over k nets converge, the Gromov-Hausdorff distance converges to 0. But we just argued in the previous proposition that if we have arbitrarily fine nets whose Gromov-Hausdorff distance converges to 0, then the original spaces have to have Gromov-Hausdorff distance converging to 0. So k and m arbitrary. And the previous proposition I think we're done. Along the subsequence. Questions? Okay, so that's somehow the big compactness result. And it's this very abstract thing where, I just try to make I try to choose a subsequence such that the distance, I choose a subsequence of the metric spaces and a dense set of points. Well, I mean, you get the ordering in the order of the proof. So I choose a dense set of points in each subsequent, in each of the metric spaces, and then I choose a subsequence of the metric spaces along which the distances between pairs of points in the corresponding pairs of points in the dense subsequences converge. And then I sort of define that to be the limiting distance to be a distance on the natural numbers. And then by quotienting and completing, I get some abstract space, which is the abstract Gromov-Hausdorff limit of the sequence of spaces. Great. And okay, so we would like a version of all this, which works. So I remember this would be great if we were dealing with just compact metric spaces, but when k is negative, the CDKN spaces can in fact be non-compact. And so we'd like a version of all this for non-compact spaces. And I already kind of hinted at what the trick was, what the difficulty was with this example from last week, that if you have a tube that has one diameter, if I go off to infinity along one handle, and a different diameter or a different radius if I go off to infinity along another handle, then depending on how I take the limit, I could have that the limit of this thing is itself, or I could, if I keep sliding this thing to the right, the limit could be the big cylinder. If I keep sliding the thing to the left, then the limit could be the small cylinder. And so when I want a notion of Gromov-Hausdorff convergence for non-compact sets, I somehow need to say how I'm going to take the limits. And so the idea would be that you fix a sequence of points, x1, x2, and so on. And I say what those points are supposed to correspond with in each of the spaces along the sequence. And so then if these points go off to the left side, I'm going to get this limit. If I chose a sequence of points which goes off to the right side, I would get this limit. And if I chose a fixed sequence of points, I would get this as the limit. So this is the idea behind pointed Gromov-Hausdorff convergence. And so let me give a definition, pointed Gromov-Hausdorff convergence. So if I have a sequence of metric spaces and a distinguished sequence of points in them here, so Pn is an Xn, I'm going to say that Gromov-Hausdorff converges to a limiting space x infinity, p infinity, if and only if for every small radius, small size, and large size, there exists a number depending on the two radii, such that if n is bigger than that number, there exists a possibly discontinuous map. I mean, I had all these different definitions of Gromov-Hausdorff convergence. But so Fn is going to be a map from the ball of radius r, the little radius around Pn, boy, I've made a mess of things in my notes. The ball of large radius r around Pn into the putative limiting space, such that three things happen. So first of all, this map should take the distinguished point Pn in the sequence to the distinguished point in the limit. So these maps all fix Pn, or they all fix Pn to be P infinity. Secondly, the distortion of the graph of Fn well, it's the distortion limited to the ball of radius r around Pn. So in other words, it's the supremum of x and x prime in the ball of radius, and it should be capital R, around Pn of the distortion of distances. So dn x prime to d infinity fn of x prime is less than the little variable. And finally, point C rather, is that the ball of radius big R minus little r in the limiting space should be contained in a little r neighborhood of the image of the large ball in the finite space. So this is like being an epsilon isometry with size epsilon equals r, but I don't ask for that to hold globally. I ask for it only to hold on these large balls. And the point is that the n here is uniform. It depends only on the smallness little r of the error term and the largeness capital R of the size of the ball. Questions?
So what do you mean by R on the exponential?
What do I mean by what?
Little r on the power.
This here?
Yeah.
Yeah. Okay. So that's the union of the balls in the limiting space of radius r around all x in the Fn image of the big ball. Right, so it's the R neighborhood. You take this set and you enlarge it by R.
Yeah, I require it. Sorry.
Yeah, no problem. And actually, I think that again, if we were willing to restrict our attention to length spaces, I think that it might be the third condition might be possible to state the third condition in a slightly simpler way. So Baraga, and Ivanov have an exercise which says that this actually, if the limiting space is a length space in this definition, and a sequence Gromov-Hausdorff converges to it, then it's true that the large balls converge around the distinguished points. So the BR, PN, Gromov-Hausdorff, now these would be this would be in distance dn, and this would be in distance d infinity. Right. So somehow this is implicitly what you want, but if you want to allow non-length spaces, then you need to deal with this slightly more general thing. So somehow you're thinking about these sigma compact spaces where the space is a union of arbitrarily large balls, and you center the balls at this point. Remember in this case, it was important where do we center the balls, because we might get this or this depending on where we center the balls as we take the limit. So I should have, for better consistency with notations, I should call these points P1 up to Pn and so on. Okay. And as usual, if this, just as we saw for subsets of a given metric space, Hausdorff convergence of the subsets to a limit implies Hausdorff convergence of the subsets to the closure of the limit. It's true that if you have a sequence converging to a limit, then it also converges to the completion of that limit. And so we might as well only deal with complete spaces, because we can't distinguish an incomplete space. We can't distinguish an incomplete space from a complete space using these notions of convergence. And one more result from, okay, I want a couple more results. I want to quote at least a couple more results from Baraga, and Ivanov. So if I have two different pointed limits, complete pointed GH limits of a sequence of the same sequence, then if one of them is boundedly compact, then the other one will be boundedly compact as well. In other words, if it has the Heine-Borel property. And actually, never mind that. Never mind. So is that then x and x prime are pointedly isometric. I.e., there's an isometry with fp equals p prime. So again, so we proved earlier that on compact sets, Gromov-Hausdorff convergence defined a metric between isometry classes of compact sets. And what this theorem is telling us is that remains true for if we do non-compact sets and we use pointed Gromov-Hausdorff limits. It's again an isometry provided we restrict to spaces that are, I mean, it's again a metric, it's a notion of convergence between isometry classes, at least provided we restrict our attention to isometry classes of pointed metric spaces that are boundedly compact. And the proof, so I'm just going to say, I'm not going to say much about but the proof is the same as before. It's similar to showing DGH metrizes isometry classes of compact metric spaces. And by the way, if you think back to that proof, I used compactness in two ways in the proof. First, I said, well, X is compact so that there is I can find a countable dense subset of X. But that would have been true for X Polish. I used compactness the second time when I said the images under that of that dense set under these epsilon isometries admits convergent subsequence in Y. For that, I needed compactness of Y. And so that second use of compactness is more fundamental. And then I used a diagonal process to show that I had an isometry first between these subsequences of dense sets and then eventually between their limits. So you do the same thing here, except there are two parameters to worry about, the parameter little r and big R. And so you have to use the diagonal process twice. So in other words, you fix a big R, and you use a diagonal process to extract a limit from a subsequence as little r goes to 0, and then you use a diagonal process again to extract a limit of subsequence as big R goes to infinity. Okay. And with that, we can then extend, by a similar thing, we can then extend our pre-compactness result to pointed, not necessarily compact spaces. So this is the Gromov pre-compactness theorem for non-compact, but still boundedly compact metric spaces. So let script X be a class of pointed boundedly compact metric spaces. And what takes the place of the uniform total boundedness is that the number of balls for a given little r and big R, you should have a little R net consisting of a bounded number of balls where the bound can depend on little r and big R. So there's going to exist a capital N depending on the two parameters, such that for every pointed space in the class, the ball around the preferred point of radius big R admits a little r net points rather. And then the conclusion is that script X is precompact in the sense that, i.e., any sequence in script X admits a boundedly compact Gromov-Hausdorff limit. Pointed Gromov-Hausdorff limit. And basically, it's the same thing. You redo the previous precompactness proof using an extra diagonal argument. First as the the distortion or whatever of the epsilon isometries, the little r isometries goes to 0, and then as the size capital R of the big bar goes to infinity. Redo previous argument. Applying diagonal process. First, as r equals 1 over k to 0, and then as capital R equals j goes to infinity. So what's the interest of this for us? Here's the the thing that I tried to state as a meta theorem a week ago. For every fixed pair of parameters, curvature and dimension parameters, the class of CDKN spaces is pointedly well, okay. So it actually is pointedly GH compact, but we can't quite show that yet. Today we can only show it's pointedly Gromov-Hausdorff precompact. So in other words, the limit will be a metric space, but we haven't yet said what the measure on the limiting metric space should be in order for the limiting metric space to inherit the curvature dimension bounds of the approximating sequence. So our goal for next week will be to eliminate the pre part of this compactness result. But anyhow, let me just prove the pre-compactness, and this is very easy. So let xn dn be a sequence in CDKN and fix Pn in the sequence in xn for every n. And also, so given r, little r, and big R, the Bishop-Gromov estimate basically told us that if we take some ball of large radius capital R, and then we look at small balls inside that big ball of radius little r, that the mass of those little balls can't be too small. The mass of because the ratio of the mass of little balls to some expression in little r dominates the mass in the large ball divided by the same expression in big R. We get that the mass of little r around Pn is controlled by the mass of big R around Pn by some and some constant. What should I call the constant? Let me call the constant n, where the constant depends on little r and big R, and it depends on k and, sorry, let me call it capital N. It depends on k and n, but it doesn't depend on, say, it doesn't depend on the space, except that it satisfies these conditions. It doesn't depend on the choice of point in the space. So there exists this constant capital M of R, K, and N. And that tells us that this is for all balls little r around any, around any xn, provided it's contained in the ball of radius big R around Pn. And therefore, there exists, so the diameter of these balls is 1 over 2r. So there exists a 1 over 2r net in B capital R around Pn with the cardinality of this 1 over r net being at most this capital N, because well, it's the usual story. You take a maximal collection of disjoint balls, and then if you double them, they have to cover the space because of by maximality. So maybe it's a 1 over 4r net. Whose cardinality, or maybe it's a 1 over r net, sorry. So there's a 1 over r net whose cardinality is at most 1 over this capital M, because when the balls are disjoint, the smaller balls that are disjoint from each other, their measures can't add up to more than the measure of the larger ball. And so now the theorem applies, because the theorem said, as long as I have, oh yes, we also checked that CDKN guys are boundedly compact. And then the theorem says, as long as I have this uniform N such that the ball of radius big R contains a little r net with no more than that bounded number of points, then I can extract a Gromov-Hausdorff limit. Did I never finish stating the theorem? Oh yes, then X is pre-compact, so any sequence admits a boundedly compact pointed GH limit. So by the theorem, some subsequence of xn, dn, pn converges to a boundedly compact pointed GH limit. Great. So in this sense, the set of CDKN spaces is in this pointed Gromov-Hausdorff sense, it's pre-compact, and hopefully next week we'll show it's actually compact, so that in some sense it contains the completion of all, say, Riemannian manifolds with lower Ricci bound k times dimension -1 and upper Ricci bound capital N. Are there questions? So let me stop the recording.